Have you ever flipped a coin? Really thought about what was happening in that split second when the coin was spinning in the air? It feels random, doesn't it? 50-50, heads or tails, we all accept that. We build our entire understanding of probability and luck on that simple idea. But here's the thing. What if I told you that randomness doesn't actually exist? What if the moment you flipped that coin, the universe didn't decide on a result? What if the universe did both? Think about that for a second, not just as a metaphor, not as a maybe. Physically, tangibly, both outcomes happened. You saw heads. The coin landed on the table, flat and unmoving. But somewhere in a place you can't see, touch, or hear, that exact same coin landed tails. And there is a version of you right now staring at it, wondering why they didn't get heads. You probably think this sounds like science fiction. I get it. It sounds like a plot device for a Marvel movie. But if you follow the logic of physics to its absolute breaking point, if you refuse to look away when the math gets uncomfortable, you end up in a place that is so strange, so counterintuitive, that it makes the sci-fi version look boring. This isn't about alternate dimensions where you have a goatee. This is about the structure of reality itself. We are going to explore why the universe must be a multiverse. Not might be, not could be, must be. We're going to follow the path laid out by physicist David Deutsch and the many worlds interpretation of quantum mechanics. We're going to strip away the comfort of probability and see what's left when you realize that nothing is ever random. And by the end, you're going to realize that you aren't just one person living one life. You are a ripple across an unimaginably vast ocean of existence. So, how did we get to a point where believing in infinite copies of yourself is actually the rational choice? To understand that, we have to go back to the beginning of the 20th century. We have to go back to a time when physics shattered. Imagine it's the 1920s. We've just figured out that atoms aren't the smallest things, there are electrons inside them. But there was a problem. These electrons didn't behave like little rocks or planets. They behaved like waves. This is the birth of quantum mechanics, and the fathers of this field, people like Niels Bohr and Werner Heisenberg, they were brilliant, but they were confused. They were seeing things that shouldn't be possible. Let me give you a concrete example, the double-slit experiment. This is the classic scenario. Imagine you have a wall with two tiny slits cut into it. You fire a stream of electrons at the wall. Behind the wall, you have a detector screen. If the electrons were like tiny bullets, you'd expect to see two distinct strips on the screen where the bullets went through the slits, right? Simple. Logical, but that's not what happens. Instead, you get an interference pattern, a series of stripes. Bright bands, bright, dark. This is what water waves do when they pass through two slits. They mix and interfere with each other. But here is the weird part. Even if you fire the electrons one by one, a single electron leaving a pattern like it interfered with itself. This drove the physicists crazy. So they came up with the Copenhagen Interpretation. They said, okay, look, an electron is a wave of possibility until you look at it. The moment you measure it, the wave collapses and becomes a particle in one specific spot. It was a patch, a band-aid. It said, the math works if we just accept that reality is fuzzy until we observe it. And for a long time, that was enough. It allowed us to build computers, lasers, and GPS without worrying too much about the philosophical implications. But wait. Let me say that differently, because the collapse idea is actually kind of insane if you stop and think about it. It implies that you, the observer, have a special power. that the universe is waiting for you to look at it before it decides what to be. It puts consciousness right at the center of reality, and that didn't sit right with everyone. In 1957, a young student named Hugh Everett III came along. He looked at the math, the Schrödinger equation, which describes how these quantum waves move. He noticed something everyone else had chosen to ignore. The equation never mentions a collapse. It's smooth, it's continuous. It describes the wave spreading out, getting bigger, interacting with other waves, but it never stops or pops. Everett asked a simple, dangerous question. What if we take the math literally? What if the wave never collapses? If the wave never collapses, then every possibility contained in that wave continues to exist. When the electron goes through the slits, it doesn't choose. It goes through the left slit and the right slit. But here's the kicker, so do you. If you build a detector to see which slit it went through, you become part of the wave. The detector becomes part of the wave. There is a version of the wave that saw left and a version that saw right. And these versions continue existing, effectively splitting off from each other. They didn't call it the multiverse back then. Everett called it the relative state formulation. It sounds boring, but it was a grenade thrown into the foundation of physics. He was essentially saying that the universe is a massive, ever-expanding tree of possibilities, and we are just riding on one tiny branch, unaware of the rest. Now, this is where most people stop. They hear infinite universes and they check out. They say, that's unprovable, that's metaphysics. You can't test it, and for a long time that was the standard critique. But then along came David Deutsch. Deutsch is a different kind of physicist. He's a bold, sometimes abrasive thinker who refuses to compromise on reality. He looked at Everett's idea and he asked the question that would cement the many worlds theory as the only one that makes sense. He asked about computers, specifically quantum computers. You've heard of quantum computers, right? They are supposed to be impossibly fast. They can break encryption that would take a normal supercomputer millions of years to crack. But here's the thing that nobody really explains: where does that power come from? Let's use a concrete example. Imagine you have a maze. A normal computer trying to find the exit would try one path, hit a wall, go back, try another path. It's serial, it's one step at a time. A quantum computer, on the other hand, explores all paths simultaneously. That's the common explanation. It's parallel processing. But think about that. Where are these other paths being calculated? If you have a quantum chip sitting on a table in a lab and it's made of, say, 100 qubits, quantum bits, the amount of information it processes is 2 to the power of 100. That is a number so large there aren't enough atoms in the observable universe to write it down. 1, 2 followed by 30 zeros. So here's the expectation: the computer is just a fancy calculator. Here's the reality: if the computer is just using the atoms in this universe to do the work, it would have to be hotter than the sun. It would require more energy than exists in the galaxy. It physically cannot fit the calculation into the spacetime of our single universe. David Deutsch looked at this and said, no, the computer isn't doing the work alone. The only way the math works, the only way the physics makes sense, is if the computer is exploiting the other worlds. The quantum computer isn't just calculating in this room. It is outsourcing the work. It runs the calculation in this universe where the qubit is 0. It runs the calculation in another universe where the qubit is 1. It runs the calculation in a third universe where it's 0 and 1. And it does this for billions of universes simultaneously. Then it brings the answer back to us. Now here, S where it gets beautiful. The only way the computer can bring the answer back is if the different versions of the computer in the different universes interfere with each other. Just like the water waves in the double-slit experiment, they share the information through interference. If the other universes weren't real, if they were just theoretical possibilities, there would be nothing to interfere with. The computer wouldn't work. The fact that quantum computers do work and we have built them, they exist, is proof that the other universes are there, tangible and loaded with processing power. Think about it. You are using the resources of parallel Earths to solve a math problem. That isn't just a theory, that is an engineering necessity, but I know what you're thinking. If this is true, why don't I see it? Why don't I feel myself splitting? Why does my life feel continuous? That's a fair question. And this is the next layer of the deep dive. It comes down to something called decoherence. Don't worry about the jargon, just think of it as noise. Imagine you are at a loud party. You are trying to hear a whisper from the person next to you. It's impossible. The noise of the music, the clinking glasses, the laughter, it all drowns out the subtle signal. Quantum splitting is a very delicate, quiet process. It happens easily with isolated things like a photon in a vacuum or an electron in a supercooled chip, but you are big. You are hot, you are made of trillions of atoms banging into each other constantly. You are the loud party. The moment a quantum split happens, the environment around you, air molecules, photons of light, heat, immediately reads the result. They interact with you. And because the environment is so messy and vast, the two versions of reality, where you saw heads and where you saw tails, very quickly lose the ability to talk to each other. They decohere, they separate. It's like radio stations drifting apart on the dial. The signal is still there, but your radio is no longer tuned to hear the other one. You don't feel the split because you are embedded in the split. You are part of the noise. This brings us to a really profound implication. If the multiverse is real, then probability is a lie. When you say there is a 50% chance of rain, you aren't describing the future. You are describing your own ignorance. The future has already happened in a sense. There is a version of the future where it rains and a version where it doesn't. Both are real. The 50% isn't a property of the universe. It's a measure of how many yous are going to experience rain versus sunshine. This sounds like it removes free will, doesn't it? If every choice creates every outcome, does it matter what you choose? Here, S what you'd expect. If everything happens, nothing matters. But that's not what happens. Because even though the universe is split, the laws of physics remain constant. Gravity is still gravity. Logic is still logic. You can't choose to fly by flapping your arms, even in a multiverse. The split is constrained by what is physically possible. Your choices still matter because they determine which branch of reality you get to experience. You are the captain of your own specific ship, even if there are millions of other ships sailing in different directions. So, what does this all mean? Why should you care about a bunch of invisible universes and quantum computers? It changes everything about how we see ourselves. For centuries, we have suffered from a kind of cosmic loneliness. The idea that we are a single speck of dust in a vast, dead universe. The idea that when we make a mistake, the path not taken is lost forever. It's gone into the void. But the many worlds interpretation tells us that nothing is ever truly lost. Every choice you've ever made, the job you took, the person you married, the time you turned left instead of right, all of those paths exist. They are happening right now. This connects to something David Deutsch calls the principle of optimism. If there are infinite variations of humanity across the multiverse, then it is inevitable that some of them survive, some of them solve the climate crisis, some of them cure death, some of them become immortal. And crucially, if they can do it, then so can we. We are not separated by physics, we are only separated by information. We are just a variation of the humans who succeeded. This perspective shifts the focus from fate to problem solving. If we fail, we aren't doomed by the universe, we just took a wrong branch, and we can backtrack. We can learn from the branches where we succeeded, and this brings us to the 3 for 2 moment I promised you. This single insight, the reality of the multiverse, explains 3 seemingly unrelated things. The double-slit experiment. It explains why particles act like waves without needing a mysterious observer effect. Quantum computing. It explains where the processing power comes from. The fine-tuning of the universe, why our universe is so perfect for life. It's not that a creator tuned it, it's that if it weren't tuned, we wouldn't be here to ask the question. We are just in the universe that worked, one of millions that didn't, one theory. 3 explanations, that is the power of a good physical theory. But wait, let me recalibrate here. I don't want to make it sound like this is all solved. This is the frontier. We are still figuring out how to test these boundaries. But the fact that the math works so beautifully that it unifies these disparate fields, it's hard to ignore. Think about your day today. You woke up, you had coffee, you went to work. It felt mundane, it felt ordinary. But if you look at it through the lens of the multiverse, every moment was a branching point. Every interaction was a delicate dance of quantum decoherence. You are not a static object moving through time. You are a process. You are a growing, expanding tree of consciousness. It makes the world feel bigger, doesn't it? It makes the quiet moments feel heavy with potential. So where does this leave us? We started with a coin flip. We thought it was chance. We found out it's reality splitting. The reason I wanted to share this with you isn't just to blow your mind. It's because understanding this changes your relationship with the unknown. When you look up at the stars at night, you aren't just looking at empty space. You're looking at the canvas where infinite histories are being written. Every photon that hits your retina is a traveler from a distant star, and perhaps from a distant universe, interfering with your reality in the smallest, subtlest way. David Deutsch often talks about knowledge as a physical thing. He says that the growth of knowledge is the most significant phenomenon in the universe. And if the multiverse is real, then the growth of knowledge is exponential across all of reality. We aren't just learning in isolation. We are part of a vast, cosmic network of discovery. When you solve a problem here, you are solving it for every version of yourself that follows. When you create art, when you build a bridge, when you love someone, you are adding to the structure of the multiverse. We used to think the Earth was the center of everything. Then we realized it was just one planet in a solar system. Then we realized the solar system was in a galaxy, and the galaxy in a universe of billions of stars. The many worlds theory is just the next step in that humbling yet exhilarating expansion of our perspective. It's the realization that even the universe isn't the limit. There is no end to this. There is no final frontier where we stop and say, okay, we found it. Because every answer we find just generates more questions. Every discovery splits our future into more paths that need to be explored. Science is an avalanche. It starts with a small pebble, a question, a curiosity. It hits the snow and it starts to move. It picks up speed. It gathers more snow, more rocks, more mass. It becomes unstoppable. The realization that the universe is a multiverse, that is a boulder hitting the slope. We are just watching the beginning of the slide. We are seeing the physics of the 20th century crash into the philosophy of the 21st, and it's taking us all with it. So the next time you flip a coin or make a choice or wonder what if, remember, you don't have to wonder. The what if is real, it's out there, and it's waiting for you to catch up.